This is section 5.2, which is proving trigonometric identities. We're going to talk about proof strategies, proving identities, disproving non-identities, and identities in calculus. Okay, so there's a lot of general strategies that are listed in this section. So the first set, it says, so the proof begins with the expression on one side of the identity. The proof ends with the expression on the other side. So with verifying proofs or verifying identities, what your goal is to get the left-hand side of the equation to equal the right-hand side. So you're showing through a series of equivalent steps, and that's what it shows for number 3. So the proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to its preceding expression. So this is one of those times that the process is more important than the right answer. You actually know what the answer is to these problems. It's on the other side of the equation. So you're just through a series of steps showing that one side of the equation equals the other. And so you need to be very careful and you need to show every single step along the way. There's no big jumps or assumptions as you go from one expression to the next. Okay. So some other strategies: begin working with the more complicated side and work towards the less complicated side. So tackle the side that's a little bit more complicated first. If no other move suggests itself, so if you get stuck, convert everything into sines and cosines. That's always a good strategy. So if you're not sure what to do, turn everything into sines and cosines. And then you can combine fractions by combining them over a common denominator. I'd like to also add you can break apart fractions into two separate fractions. So looking for chances to either combine or separate depending on what your goal is. And then I'm going to add a fourth one here. And the fourth one is try something. So where a lot of people get stuck is they're staring at it for a long time and they don't know what to do. It would be better to try something and maybe hit a dead end and and then have to go back and try something else than to just stare at it and not start because you're not sure what to do. So always try something, attempt it. Start substituting in different things and seeing if that's going to give you more insight onto the problem. Okay, so here's our first example. This is setting up a difference of squares. So on this one, I would start with the left-hand side. They look equally complicated, but on the left-hand side, I don't like the 1 minus cosine. I don't like to have a plus or minus in the denominator. And the thing that you don't want to confuse this with, 1 minus cosine is not the same as 1 minus cosine squared. So this is not a Pythagorean identity. But I can turn it into one if I multiply both sides by 1, or not both sides, top and bottom, by 1 plus cosine. It's hard to write small. Let's try that again. There we go. Okay, so I'm going to multiply the left-hand side, top and bottom, by 1 plus cosine. So that's going to give me 1 plus cosine times sine over, and these are difference of squares now in the denominator. So if I multiply them out, I'm going to lose those middle terms. I'm going to get 1 minus cosine squared. Now I have a Pythagorean identity, and I know that 1 minus cosine squared is equal to sine squared. So I can write this as 1 plus cosine times sine over sine squared. And we know sine squared is just sine times sine, so I can cancel this sine with one of the sine times sine. So then I have 1 plus cosine over sine, and you will see that equals the right-hand side, so we're good, and we verified it. Okay, here's our next. Oh, this is more general strategies. So recognizing difference of squares, even when it's like on our previous problem, 1 plus cosine times 1 minus cosine, that's a difference of squares. So recognizing that difference of squares and using it to apply to the Pythagorean identities are going to be very helpful. And it says to always be mindful of the target expression. So try to figure out what you're trying to turn it into, and that's going to help you along the way. Okay, so here's the next one. So we have sine to the 5th times cosine squared equals sine times cosine squared minus 2 cosine to the 4th plus cosine to the 6th. Okay, so clearly on this one, the right-hand side is more complicated, so I'm going to start over here. So I have a sine here, and then I notice in the parentheses, all three of those terms have cosine squared in common. So I'm going to factor out a cosine squared, which is going to leave me with 1 minus 2 cosine squared plus cosine to the 4th. Now, hopefully you recognize that that is quadratic. It's not quadratic, it's in quadratic form because we have to the 4th power, we have squared, and then we have no x value. So I'm going to rearrange this a little bit. So I'm going to write sine of x, cosine squared, and then I'm going to rewrite this in how we're used to seeing it. So cosine to the 4th minus 2 cosine squared plus 1. So think about it as x to the 4th minus 2x squared plus 1. So how would we factor that? Well, we would say what multiplies to positive 1 and adds to negative 2, that would be minus 1 and minus 1. And then because this is to the 4th power, it'd be x squared minus 1 and x squared minus 1. So I'm going to turn this into, instead of x, I'm going to put the cosines. So this is going to be cosine squared minus 1 times cosine squared minus 1. Now, cosine squared minus 1, that should remind you of the Pythagorean identity, but it's not sine squared, it's actually negative sine squared. So this would be, and notice how I'm writing every single little step. So this would be negative sine squared, and this would be negative sine squared. But when we multiply it all out, we know a negative times a negative is going to turn positive. I have sine squared, so that'd be sine to the 4th, times sine would be sine to the 5th, sine to the 5th times cosine squared. And you can see that is equal to our left-hand side of our equation, so we are done. Okay, here's our next one. We're proving tangent of x plus cotangent of x equals secant of x times cosecant of x. So this would be one maybe to turn stuff into sines and cosines. So I'm going to write this as sine over cosine plus cosine over sine. So I have two fractions. I want to combine them into one, so I'm going to get a common denominator. So that means I need to multiply this fraction by sine and this fraction by cosine, which is going to, on the top, give me sine squared plus cosine squared. And then my common denominator was sine times cosine. And then we know sine squared plus cosine squared is just 1. So this would be 1 over sine times cosine. And then I can break this up into multiplication. So I could say 1 over sine times 1 over cosine, which is going to be cosecant times secant, which is equal to secant times cosecant. Okay, here's our last one. So this is an example of working with both sides. So it says to prove this identity, you can see looking at both of these sides, they're both probably equally complicated. And sometimes you will need to work with both sides of your equation. So on this one, I would recognize that cotangent squared can be turned into cosecant squared, minus 1, using our Pythagorean identity. So this would be cosecant squared minus 1 over 1 plus cosecant. Okay, and then I recognize that we have cosecant in the numerator and the denominator, so I could turn the numerator, I could actually factor that because it's a difference of squares. So I can make it cosecant plus 1 and cosecant minus 1 over 1 plus cosecant. So then the 1 plus cosecant can cancel with the cosecant plus 1. So now I have on the left-hand side, I have cosecant of u minus 1. So I'm going to stop there on the left because I feel like that's pretty simplified. Now I'm going to move to the right, and I'm going to turn everything into sines and cosines. So cotangent would be cosine over sine. Secant would be 1 over cosine. And tangent would be sine over cosine. Now I'm going to distribute that fraction. So then I'd have cosine over sine cosine minus cosine sine over sine cosine. Oops. Sometimes I forget my angle there. Okay, so in this first fraction, I can cancel the cosines. And here I can cancel the cosines and cancel the sines, which means it's just going to turn into 1. So this is going to be 1 over sine minus 1. And we know 1 over sine is cosecant. So then we show that those two are equal. So that's an example of taking both sides and simplifying them so that you can show that they're equivalent. Okay, let me know if you have any questions.